Good morning, everybody. Welcome to the Friday seminar. It is my great pleasure to continue the Friday seminar series with another international presence. A few weeks ago, you heard Dr. Novikova from École Polytechnique and about the optical material. And now today we have from across the Atlantic, another speaker from Europe, and this is Dr. Andrea Canessa. So Dr. Canessa is an assistant professor. He got his PhD in bioengineering from University of Genova. And he started with computational neuroscience work. And today you will also hear about neuroscience. Some of you who work with Dr. Schumer's know about Dr. Schumer's work. Dr. Canessa did a lot with vision and visual motor interactions. And then he has also been looking at virtual reality environments in which you can have interactions and being able to study movement disorders in this kind of engagement in this virtual reality environment. You will notice from his talk that he is using a lot of technology and techniques to basically get an assessment of what the body and the brain is doing. So he uses EEG, he uses Gait markers to see kinematics, and so many of these different aspects. So to get a read of what is going on in the normal brain and also under pathophysiology. And in particular, he is interested in looking at Parkinson's. And of course, you can also do a write to the brain, just like you do the read. And one of the ways you can do a write to the brain is by doing stimulation on the brain and in changing the activation, and that is deep brain stimulation. And so Dr. Canessa is going to talk to us about deep brain stimulation in movement disorders, clinical effects and pathophysiological mechanisms. I'm delighted to have him join us.
Thank you for the opportunity to present you one part of my work, and hello everybody. And today we speak, I will tell you about deep brain stimulation in movement disorder. In reality, in Parkinson disease, so one of the movement disorder, and present some study that we performed in the recent years about the using of deep brain stimulation in Parkinson disease. Okay, so Parkinson disease. Parkinson disease affects 6 million people worldwide. And together with essential tremor, is another movement disorder, is the most common movement disorder. Parkinson disease is due to so the main alteration of Parkinson disease is the degeneration, so the loss of dopaminergic neuron in the substantia nigra pars compacta, that is a deep and small area within your brain, within our brain, and this degeneration causes a consequent reduction of dopaminergic projection in the striatum. Substantia nigra and striatum are two of the main nodes of the Basal Ganglia circuit that we saw later. The reduced dopaminergic input, so it's considered the cause of the motor manifestation of this disease that principally show bradykinesia, so slow movement, rigidity, so your muscles are too stiff, resting tremor, and also postural and gait impairment. From the late 60s, so 1970, from the 1970, the mainstay treatment of PD is dopaminergic replacement therapy with levodopa. Levodopa is a dopaminergic agonist, is a precursor of the dopamine that succeeds in binding the dopaminergic receptor. So it's a sort of substitute of dopamine and is and allowed to re-equilibrate the level of dopamine in Parkinson's disease brain. And this therapy has been proven safe and effective, in fact, in controlling most of the symptoms in the early phase of the disease. However, if the dopaminergic replacement therapy is useful in the early stage of disease, maintaining the disease, so the symptoms of Parkinson, well controlled in what is called in an on state. So there is some small fluctuation of the symptoms that are well controlled. In the late stage of disease, the therapy, so the dopaminergic therapy, could provoke also some treatment-resistant motor features. So you have a sort of you have an increase of the fluctuation of the symptoms, and that could cause dyskinesia, so dyskinetic movement, so irregular and involuntary movement of your body, can increase postural instability, could produce freezing of gait, so this an unexpected stop of the capacity of walking, and finally could lead also to falls. So for this reason, dopaminergic therapy in the late stage of disease is not so it's not so effective. Deep brain stimulation comes in. What is deep brain stimulation? Deep brain stimulation is a surgically implanted electronic device used to modulate the neuronal activity in particularly brain region of specifically one or two electrodes, often referred as leads, are placed in a specific target in the brain using different stereotactic neurosurgical technique. The leads are then connected to a small implanted pulse generator, IPG, which usually resides under the skin in the chest, like the same as the heart pacemaker, and contains all the electronics that generate stimulating pulses, together also with all the battery and power system. In the photo, you can see a sketch of what is, you have the pulse generator in the chest, and you can see the leads that are inserted inside the brain, targeting to specific region. In this case was the subthalamic nucleus. As I said, deep brain stimulation is an effective treatment for not only for Parkinson's disease, for a wide range, so also for essential tremor, for dystonia, for obsessive compulsive disorder, and up to epilepsy and whatever, and other. Here you can see that the proportion of DBS surgery is for the more than 60% covered by Parkinson's disease. So this is the reason why I speak about Parkinson's disease today, because it's the most representative population. After 2 years, quality of life in DBS patients significantly increased, and levodopa could also be reduced on average of 39%. So it's a really effective treatment, DBS. And many studies also demonstrate that the suppression of PD symptoms in upper and lower limb was presented also after a period of also 5 and 10 years after surgery. So it's a long-term effective therapy. But the problem is that, however, there could be also the concomitant deterioration of gait. So there could be some problem related to gait and posture, and also to cognition. So DBS is an effective therapy, but it presents also drawbacks for Parkinson's disease, because it has a limited efficacy in ameliorating gait problem, and with the possibility also to show long-term adverse effect, adverse non-motor effect. Typically, in Parkinson's disease, in essential tremor and dystonia patient, the principal DBS target are the ventral intermediate nucleus, VIM, of the thalamus, depicted in purple in the left figure, the subthalamic nucleus, in gray in the left figure and in orange in the right, and the globus pallidus part interna, so the internal part of the globus pallidus. For what concerns the instrumentation behind DBS, we saw that there is an impulse, an implanted pulse generator, and the leads. For what concerns the implanted pulse generator, actually there are different type. There are different companies that produce implant IPG, and so implanted pulse generator. There is the Boston Scientific with the Versys PC or Jevia. There is the Abbott, previously St. Jude, with the Infinity stimulator, and Medtronic, that actually is with this Percept PC, that substitute the previous Activa PC. All these device come with also with the PC or laptop software where the clinician could try to program the stimulation. The other part, important part of the DBS, is the leads, so the electrodes. Since the advent of deep brain stimulation, something like 30 years ago, more than 30 years ago, there has been little changes to the classic deep brain stimulation electrodes proposed by Medtronic, which consists of a flexible 1.27 millimeter diameter cylinder with a series of 4 platinum iridium cylindrical contacts at the distal end of the electrodes that are spaced with 1 or 0.5 millimeter each other. Okay, then how DBS is performed? So how we can how the leads, the electrodes are inserted in the brain? Well, to implant the electrodes, the patient has to go through a surgery, obviously, neurosurgery operation, and but although details regarding the surgical technique may vary between center and center, so between hospital, all combine a stereotactic technique with detailed image guidance of the patient. So stereotaxis is a minimally invasive procedure, surgical procedure, that make use of three-dimensional coordinate system to accurately locate a precise target, for example, the VIM or the STN or the GPI, as we saw before, within the brain. Then electrodes are implanted into the target by means of a stereotactical surgical procedure, together with electrophysiological recording. Okay. So, firstly, a stereotactic head frame is placed on the patient under local anesthesia in the operating room. Then a CT scan, so a computer tomography or a magnetic resonance imaging is obtained. These allow to identify the reference frame of the patient, and based on the location of the structure that we want to target, the planning of the insertion of the lead of the electrode is obtained. As I said before, together with these, in the stereotactic surgery, make use also of electrophysiological recording. Why? Well, to be sure of the precise location of the leads, because we have to be perfectly sure that the leads is targeting the right nucleode. So if we want to stimulate the STN, we have to be sure that the leads is within the STN, so the subthalamic nucleus. Multiple micro recording, up to 5, the standard procedure, are sequentially carried out at different depth. So you insert a micro electrodes, you move from 15 millimeters up the target, you start to move down 1 millimeter by 1 millimeter, and to get with this technique, with this procedure, you try to optimally track and select the right depth along the trajectory of the lead to locate the right target. And you do this procedure listening or looking at the activity of the neural population that you encounter step by step. As you can see in the figure, a different, also varying also by 1 millimeter, the position of the electrodes along the trajectory could cause a really huge changes in the activity recorded by the electrodes. So starting from the thalamus, the zona incerta, and subthalamic nucleus. Okay. Then, when you have reached and select the right position of the electrode, so you are right that you are choose your target, start a procedure to find the optimal set of parameters of the stimulation. Consider that for the stimulation, there are 3 typical parameters that you can vary. You can change the intensity or the amplitude of the stimulation in volts or in milliampere. You can change the frequency and the pulse width. Typical value of for this parameter are, for the voltage is something like 2.4 and 4.4 volt. For the frequencies from 130 to 180 hertz. And for the pulse width is 60 to 140 microseconds. And other than the amplitude, frequency, and pulse width, since for each leads you have 4 contacts from where you can stimulate, the next step is to find the optimal configuration of the electrodes. So selecting the from which contacts on the electrodes you want to stimulate. You can choose a monopolar configuration, so with one single contact, negative, so cathode contact, a double monopolar, or bipolar configuration. Then, okay, once you implant the macro electrodes, so you select the right position of the electrodes, the right depth along the trajectory, the right configuration of the electrodes and stimulation parameter. Another step that is done is to configure the what is so-called the volume tissue activation. So, and you configure this quantity to match the target region to prevent the how to say the spreading, okay, of the stimulation and of collateral currents outside the target. And the volume, but okay, the volume of tissue activation around the contacts that you choose depends on the electrode shape, but also on the stimulation parameter, the modality of the stimulation, so the configuration, if monopolar or bipolar, and also properties of the tissue that are surrounding the electrodes. Fortunately, for this procedure, there are a lot different new software and computational model that allow the clinician to verify the VTA, so the volume tissue activation. One is an open source, is LeadDBS. Other two are Gait, XT, and SureTune that are proprietary software from the Boston Scientific and Medtronic, but all gives you the possibility to show and to tune the parameter and tune the volume tissue activation to match the target. As you can see, for example, in the left figure, there is the leads targeting the STN in orange, and in red, you can see the model, the simulation model of the volume tissue activation for a particular configuration of the stimulator. And you can see that it is pretty much inside, located inside the STN. Obviously, the technology, so the advancement in is always running. So and now the ongoing challenge in the DBS, in the DBS leads design, is to increase the spatial selectivity of the stimulation. So to give the possibility to the clinician to perfectly adapt the stimulation to the patient. Every patient has his own head, every head has a different structure. So give the possibility to the clinician to select perfectly different parameter and configuration of the leads to match the target it would be a very effective challenge. And to address this issue with the current stimulation technology, segmented electrodes with higher spatial selectivity have already been designed. For example, there is one novel electrodes designed by Boston Scientific that can control independently the stimulation parameter for each of 8 contacts of the electrodes. Or there is another, is a novel electrode with 32 contacts distributed uniformly around the circumference of the leads, which allowed the to steer the electric field in 4 directions. Or, for example, there is another lead with 4 rings, where each ring is composed by 3 independent contacts. Or there are another is the shape of a cross with it's the micro DBS with a really dense percentage of contacts. So all these to try to improve the accuracy on the leads, localization, and the stimulation parameters, and trying to improve the efficacy of the stimulation for each patient. Okay. Till now, I spoke about DBS as a therapeutic strategy. So it's something, as I said, it's something that came out to overcome problem due to dopaminergic replacement therapy adverse effect. But deep brain stimulation, fortunately for the neuroscience research, is not only a therapeutical strategy, because with the introduction of electrodes and the application of the electrical stimulation within the brain, not only allow the alleviation of symptoms, so it's not only a therapeutic strategy, but also present the unique opportunity to probe the function of the brain within, so looking at deep structure within the brain. So DBS, in some way, offer a portal into the workings and the dynamics of brain circuits linked to behavioral or cognition and motor aspect. In fact, during the electrophysiological mapping of the for the selection of the optimal brain target for stimulation and optimal lead location, surgeon can record activity from a single or population of neuron during rest or in response to different motor or cognitive tasks. So the ability to directly measure neuronal activity at the population level gives the investigators or researcher the unique opportunity to study neuronal network function and dysfunction in disease state. Synchronized activity and synchronized activity patterns driven by neuronal populations or neuronal ensembles can be measured in form of oscillation and are becoming increasingly recognized as a mean to drive the coordination of the brain dynamics. And so neural networks within the brain can oscillate across many frequency ranges, and different oscillatory bands have been associated with distinctive behavioral states. And what is important in the brain, oscillation is the fact that brain oscillation provide to the brain a key mechanism to share information across different areas. And this oscillation, this brain oscillation, can be measured in the form of potential, so local field potential, by different electrodes available for human clinic and research use, like, for example, the electrodes for DBS, or strip or grid of electrodes for the electrocorticography directly put on the cortex, or from non-invasive scalp electrodes like the electroencephalography. And using these methods, so DBS, LFPs, ECOG or EEG, over the past 15, 20 years, researchers have developed a new framework for understanding neurological disease resulting from disorder of network dynamics, or what is so-called circuitopathy. So the actual idea is to think as PD and PD symptoms, not as only due to a loss of dopamine. So it's not only due to a loss of dopamine, but to a derangement of multiple circuits and loops that are inside the brain. So now the current theory for Parkinson disease, so specific signs and symptoms as related to specific abnormal oscillatory synchronization in what is the so-called cortical basal ganglia thalamocortical network. that is this basal ganglia thalamo loop is a circuit that is in command of the movement, execution, planning, and where the basal ganglia are its main node, where, of course, the dopamine loss that is present in PD alter the functional organization of these circuit. The basal ganglia specifically is a group of interconnected deep brain nuclei that through the connection with the thalamus and the cortex influence the involuntary movement components. And what has been so in the last year is that excessive basal ganglia oscillatory activity across different frequency bands have been associated with different motor sign of movement disorders. For example, there is an increase in theta, so from 4-8 hertz and alpha frequency. Alpha is between 8 and 12 hertz. Have been shown in the subthalamic nucleus of PD patient during resting tremor. Elevated over synchronization in beta oscillation, so from 13 to 30 hertz, and beta burst have been observed in the STN, so in the subthalamic nucleus, and in the GPI of Parkinson patient and rest, which represent an akinesia state. Then narrow band gamma oscillation, so from 60 to 80 hertz, have been found in the STN of PD patient, both with dopaminergic medication, so in the med-on state, and during movement, and has been associated to dyskinesia and hyperkinetic state. Sorry, I forgot to move the slide. And in this figure, you can show some example of over expression of oscillation, and this came out from another opportunity that that DBS gives us, that is the ability to have deep brain stimulation electrodes externalized. So it's not only during the micro recordings during the surgery, but there is a possibility to, for a small amount of time, just for a few days after the surgery, there is the possibility to connect the leads to an external device, amplifier, to record the local field potential from DBS electrodes placed within the brain. And this approach in the last year is leading to important findings, including characterization of pathological activity, such as the beta oscillation in the subthalamic nucleus of PD patient, or how the basal ganglia are involved in movement planning and execution, and how DBS targets, so STN, GPI, are also involved in cognitive and emotional processing. Moreover, the externalization of the electrodes also allowed the oh, sorry. Allow the possibility to investigate also the role that the medication, so the levodopa, so the dopamine replacement therapy, and the DBS, so the stimulation, has on PD patient. And what has been found is that levodopa and DBS therapy were found to suppress local beta oscillation. As you can see in the left figures and the left central figure, there are the power spectral density of STN electrodes in off state, so medication off in red and medication on in black. As you can see, there is a strong reduction of the power of beta, so in the beta range from 13 to 30 Hertz with the intake of levodopa. And the same with the DBS. So when we switch on the stimulation, there is a strong reduction, with the, as you can see from the red curve in the panel B left show. Moreover, the suppression of the beta oscillation also correlate with the improvement of Parkinsonian symptom. There is a strict correlation, as you can see in the central right figure. There is a strong correlation between the improvement in the bradykinesia and rigidity symptoms with the reduction in the LFP, in the beta power. And moreover, and not only, so beta power also correlate with the severity of motor symptom in the absence of medication. As you can see, there is in the right figure, there is a correlation between the power, so the power in beta expressed by the STN, and the UPDRS score. UPDRS is a clinical scale that is used to quantify the severity of symptoms. There are different score that you can give to the patient. Okay. But okay, until recently, the majority of LFP recording are obtained, as I said, from externalized DBS leads during the perioperative period, with the connection of external amplifier. But these obviously limit the patient mobility. So it's difficult in this situation to perform recording with the where the patient move. So it could the patient or is in a resting situation, or could perform only small movement like finger tapping or moving the feet. Okay, so it's difficult in this situation to perform recording in motion. But these from what I said before, is a limiting factor because, as I said, levodopa and DBS are effective therapy, but let gait impairment and postural impairment unanswered. So it's gait impairment and postural impairment are an issue for PD, and they are not very well treated by medication or stimulation therapy. And but the problem is that gait is really important for human, because it's the way with we can move and go from one place to another. So it's and is highly debilitating for Parkinson's disease. So the study of the human gait and what happened within the brain, what is the arrangement of neural circuit that cause gait impairment in PD, is an open and challenging issue. So human gait is a complex, is complex and require the coordination of different multiple brain areas to drive the dynamic and complex behavior of motion. And this multiple brain area, so the coordinated flow of information between these multiple area is crucial for gait. And the control of human locomotion begins in the cortical region within the supplemental motor areas, premotor area and primary motor cortex, where the intentional motor programs reach the basal ganglia for refinement, and then to brainstem region and cerebellar region for then descend on toward the spinal cord. This is what is called the locomotion network. Disruption in any point, in any parts of this locomotion network can cause gait impairments. For the in PD, in Parkinson's disease, the lack of dopaminergic innervation within the striatum not only affects the basal ganglia, but also cause brain network dysfunction in many nodes of the circuit involved in the locomotion. But okay, so study the gait and the locomotion network, as I said, is a challenge issue. And now, with the availability of new investigational neurostimulational device that has the possibility to stimulate, but also to sense, to record, new studies are starting to shed light on the changes and disruption of oscillation in the basal ganglia during gait in freely moving PD patient. With the new investigational neurostimulation device, I'm referring to the Activa PC plus S created by Medtronic. This neurostimulator is, but was, because now there is the Percept-EC, but is going to enter the market now. So it's the Percept-EC really recent, but before the Percept-EC there is the Activa PC plus S, that is an evolution of the old Activa PC with the possibility, plus S, the possibility to sense, so to record local field potential. This device was a prototype that Medtronic sent to very few centers around the world. Okay, very few centers has the possibility to use this device, and me and with my colleagues in Germany at the University of Würzburg were among the few persons that has this opportunity. Then I will show you some results about, not only from us, but some results regarding the study of Gait with this new device. The particularity of this device is that it gives you the possibility to record patient also months, years from the surgery. So you have not the problem of the lesion effect of the surgery or whatever. So you can, and the patient is really free to move, because this device is totally implanted. So there is no external cable. The leads are not externalized. They are all implanted. So the patient is really free to move and can do whatever he wants. So it is a rare and really important occasion to study what happened within the brain in Parkinson's disease. Okay. For example, in one study from L and colleagues, report the 10 patients implanted with the Activa PC plus S, and they show that there is a high beta frequency power and in the STN during Gait, the high beta frequency power and bilateral, so bilateral connectivity, so communication and transfer information between the two STN is reduced during a normal gait. And moreover, they found also a reduction of the beta burst. So the beta burst amplitude and the duration of this beta burst during gait compared to resting condition. In another study by Quinn, they didn't found in reality a decreased beta power during walking. So they found controversial results.
Dr. Canessa, I am sorry to interrupt, but it's 10 o'clock and students will be going on to some other classes and all. And so we should wrap it up so we can take a few questions before they leave. So, sorry.
Okay.
Yeah, sorry about that.
So what, I have to stop or?
Yeah, finish the little topic, but students will be leaving. So we will not have many students as they start to go to their classes. So so we should stop as soon as.
Okay. But it was a few slides, but okay.
Okay, so let's finish the couple of slides. It's okay.
Okay. Here I will show that me with my collaborator in Germany performed also a study during Gait. We found no difference in the beta power, the coherence, and the cross coupling during walking compared to sitting and standing. But what we found is an interhemispheric beta phase locking synchronization during walking. We performed this study combining a lot of recording modalities. We have the STN, so from DBS, we have the EMG recording, optoelectronic system, dynamometric force plate, and universal measurement units to describe the motion. In a more recent, it's really 2020, exactly. We show also a gait-related frequency modulation. For the first time, we provide the first evidence of beta frequency modulation associated with locomotion in the STN. And we were able to perform an information theoretic analysis. We were able to identify a maximally informative frequency range whose power can accurately decode the walking state with respect to the upright standing for each single patient. And then the last study is about freezing of gait. Freezing of gait is a particular dangerous and disabling symptom of PD that limit severely the patient mobility. The particularity of this symptom is that it's unexpected. So it's like a volcano's eruption. So you don't know when happens. As you can see in the two videos, is the same patient performing the same task in two different moments. On the left, is able to perform perfectly. He succeed to open the door, walk, and whatever. On the right, you can see that he's stuck on the floor. He cannot not succeeding in performing any step forward. Okay, this is freezing of gait. It is a highly disabling symptom that causes to fall, that could lead to fall. And is really difficult to study because it's unexpected. It's also difficult to induce it in a laboratory setup. And okay. me with my collaborator, for the first time, we are able to investigate freezing gait during effective walking, so not during stepping in place or imaging walking, so during real effective walking, combining the simultaneous recording of cortical activity with EEG and subcortical activity with STN. And we found a really high decoupling between the cortex and the subthalamic nucleus during freezing. That is, okay, this is the summary. Okay, I finished.
Thank you very, very much. It's unfortunately towards the end, we were getting some really cool data and cool analysis. Yeah. But in any case, what I want to say to the students who are still there, and to you, first of all, that it was very, very informational for you to have brought us to the point with the information from the beginning to the, what happens in DBS, what happens with the levodopa, and what happens with the oscillations, and also what is the engineering components of doing that. But it's interesting that now you are in this last study that you talked about, you linked the network problems that are there with oscillations, along with the what we can see as the other pattern of movement that is going on. So is there something in specific you are able to tell from here with particular frequency bands that you can specifically talk about gait cycle things, and what particular networks might be getting affected more predominantly when you have freezing of gait? What frequency band is?
Okay, the decoupling is that I saw is in the theta alpha bands. So it's not in beta.
All right.
It's in a theta alpha decoupling. That is curious, since the majority of the study that you can find about Parkinson speak about beta.
Yes.
But we found that decoupling in theta alpha. Now we are working on this aspect, because okay, I have not had time to say this, but this study is performed on very few subjects, because okay, it's a prototype, so we have only 10 devices, and we split these 10 devices with 8 Parkinson patients and 2 dystonic patients. So we have only 8 patients performing this study. And since freezing of gait is really difficult to induce, we have only very few freezing of gait events.
Yes.
So now we are working on, as you said in where you introduced me, we are trying to include the virtual reality in this study. This is where virtual reality comes in. So we try to use virtual reality to reproduce challenging situation
that can induce the freezing.
Yeah. And then the next step will be go outside the laboratory.
Yes.
So let the patient say, okay, go.
Great.
Go whatever you want, and try to see if this theta alpha decoupling is maintained, so it's real, and probably also to enlarge the investigation to other
areas. It's fascinating, and it seems to me like we have to have some follow-up talk about the whole clinical part of it, and that would be great. I'm hoping that some graduate students and maybe some undergrads will join you for the lunch hour, that quote-unquote lunch hour, which we cannot actually share in that way, and they can follow up and ask you more questions at that time. And so that would be that would be fantastic if we can do that.